We have already discussed dual nature of radiation, in that mainly photoelectric emission and all the things related to this phenomenon were highlighted. Now, we are now moving to our next part of this chapter, that is the dual nature of matter. The matter has also the dual nature. Okay. Matter has the dual nature means matter has the particle nature, that is all very well known, and it has mainly what we have to discuss, the matter has a wave nature also. Actually, nature loves symmetry. Radiations have dual nature, so matter has also dual nature. Radiation has wave nature, that is confirmed, and particle nature we have discussed. Similarly, matter has particle nature, that is confirmed, and we are to discuss the wave nature. In this context, I first of all I am telling you, the wave nature of the matter was discovered in 1924 by a famous physicist, Louis Victor de Broglie. Louis Victor de Broglie, he actually proposed the wave nature of matter. Right. How this wave nature of matter was proposed by Louis de Broglie? Let us discuss that. We all know, actually, de Broglie considered the case of the photon, the hypothetical particle photon, and you know that by Einstein's mass energy equivalence. By Einstein's mass energy equivalence, in case of the photons, we can say the energy of the photon is given by E is equal to mc square. You can say why? Because this is in Einstein's mechanics. This equation is applicable to those particles which are moving with the speed of light, and photon is a particle which is supposed to be moving with the speed of light. So since the photon is supposed to be moving with the speed of light, so E is equal to mc square. Okay, we can consider E is equal to mc square. Now, according to quantum theory, by what Planck's quantum theory suggests, Planck's quantum theory suggests E is equal to h into c by lambda. Very well known, we have already discussed. So this is E is equal to hc by lambda. Alright, so equating, if we equate these two, on equating these two, what we shall get? hc by lambda is equal to mc square. C and C cancels, which implies lambda is equal to h by m into c. This we are getting, but after that, all I can say, although it has been this wavelength which we are getting, this wavelength is actually called the de Broglie wavelength. De Broglie wavelength, WL I am writing, de Broglie wavelength. De Broglie wavelength is the wavelength associated with the matter. Right. So de Broglie wavelength is associated, this wavelength is associated with the matter. And it was proved in case of expression was determined in case of the photons. But I just tell you, it is also applicable in case of some other particles, especially electrons. In our syllabus, mainly for the electrons, it is also applicable. So, it is also applicable in case of the electrons, and if we consider regarding the electrons, if we talk about the electrons, then we have the de Broglie wavelength is equal to h by mv. I will not write in that case mc because electrons never travel with the speed of light. That's why mv, it is slightly less than the speed of light. So h by mv, right? So this is a general expression, h by mv, or you can write h by p. Also you can write h by p. Followed? Okay. Now regarding this de Broglie wavelength, as far as this de Broglie wavelength is concerned, we have got this de Broglie wavelength. Important points. What are the important points? Let us now just see what are the important points we can write regarding it. I can write, or we can write. Number one, first, for V is equal to 0, lambda is equal to infinity. Look, that means lambda is equal to infinity has no meaning. That means the wave is not at all formed. It means de Broglie wavelength is always associated with the particles which are moving with certain velocity, with certain speed. Second point, you can write de Broglie wavelength is independent of the charge of the particle. De Broglie wavelength is independent of the charge of the particle. Alright? It is independent of the charge of the particle. So de Broglie wavelength is independent of the charge of the particle. And third point, de Broglie waves, which are also called the matter waves, de Broglie waves, right, or matter waves cannot be considered as electromagnetic wave. We cannot say that these are the electromagnetic waves. Why? De Broglie waves cannot be treated as electromagnetic waves. Why? Because de Broglie waves are not produced by accelerated charges. Actually, it is not depending upon the charge. De Broglie wave is not depending upon the charge. That's why we cannot say. We have seen electromagnetic waves, we have studied electromagnetic waves, and I think all of you remember that electromagnetic waves are always produced by the accelerated charges. But here no concept of charge, so de Broglie waves cannot be treated as the electromagnetic waves. These are some important features. Now let us find out an important point, de Broglie wavelength of an electron. Let us now find out the de Broglie wavelength of an electron. How to find it out? We have lambda is equal to h by p. Okay, kinetic energy K, capital K, kinetic energy capital K, or you can say kinetic energy, if I say here capital E, that is equal to how much? Kinetic energy capital E is equal to half mv square, that is equal to half m square v square by m. So it is equal to p square by 2m. So p is equal to root twice me. Look, kinetic energy of the electron. So we have how much? Lambda is equal to h by root twice me. Look, lambda is equal to h by root twice me. And another expression. Okay. Now you know, if an electron is moved, you can write down, if an electron is moved under a potential difference of capital V, which is called its accelerating potential. If an electron is moved under a potential difference of capital V, it's moving, in that case what will happen? In that case what will happen? The kinetic energy should be equal to E into V. We all know accelerating potential, the potential that is accelerating it. How much energy will be there? E into V. One electron. That means how much we shall get? Lambda is equal to h by root twice m eV. A very important expression which implies lambda is inversely proportional to root V. A very important expression we are getting. That is the de Broglie wavelength is inversely proportional to de Broglie wavelength is inversely proportional to the square root of the accelerating potential. Because you know h is a constant, m mass of the electron, e is charge of the electron, all are the constant. And you know that if I consider all these values, then for electron lambda is equal to 12.27 by root V angstrom. Okay, just see this 12.27 or 12.3, because all are the standard values. A very important thing I am getting. This is 12.27 by root V, and here this de Broglie wavelength is inversely proportional to the square root of the accelerating potential. A very important aspect. I think, dear students, only this much regarding the dual nature of matter will do, because this time there was an experiment, Davison and Germer's experiment, that has been omitted from the syllabus. This is why it has been reduced. I hope with this we are completing this dual nature of radiation